So today we are going to cover different pairs with current mirror loads, also known as the single stage op amp. So our circuit of interest is going to look something like this. So here's our supply voltage VDD. Go ahead and extend that over. We're going to look at this as a MOSFET circuit just because that's how I made out my notes, but obviously it could be implemented as a BJT circuit as well. So we've got some transistor here, M3. Here's our transistor M1. Here's our input voltage VN1. This transistor on the top right is going to be labeled M4. Here's VN2. And here is our tail current source, ISS. Okay. So we're not going to go into a huge amount of detail on the large signal analysis because it works extremely similarly to that of a simple differential pair amplifier, where we just had M3 and M4 as current source connected as opposed to current mirror connected. So let's talk about what a large signal, common mode signal would look like here really quickly, and then just kind of go from there, right? So if we apply the same input voltage, so let's say that we let VN1 be equal to VN2, what would we expect to happen? Okay. So I think, hopefully you guys will agree with me here, that transistor M1 would pull half of ISS, and transistor M2, which I forgot to label, my apologies, would also pull half of ISS, right? Because the gate source voltages for transistor M1 and M2 would be identical. If their gate source voltages are identical and we're not worrying about channeling modulation effects or anything like that too much, we should see that, like I said, M1 pulls half of the tail current and M2 pulls half of the tail current. Well, transistor M1 is effectively acting like it is the reference current source of our PMOS current mirror up top, right? So since it's the reference current, it stands to reason then that this guy will also be pulling exactly 1/2 ISS, and that same current will be mirrored over here. So that we'll have a 1/2 ISS, right? So surprisingly enough, that's literally all of the information that we need to figure out what our DC output voltage is going to be. Okay? So let me explain what I mean specifically by that. Okay? So let's call this voltage right here VSG 3. And just for the sake of argument, we know that the voltage measured between the supply rail and this node right here is also VSG3 because we have a diode connected transistor. Well, if the transistor M3 is carrying a particular current and the transistor M4 is carrying that exact same amount of current, they should have the exact same drain source voltage relationship as well. So we can see that V out is literally just VDD minus whatever VSG3 is. So that begs the question, well, how do we figure out what VSG3 is? We know the current flowing through it, so we can back calculate from that current what VSG3 is for a known threshold voltage, right? So effectively, we know that ID is 1/2 mu P Cox. Let's call this ID3 for sake of argument. W over L3 times VSG3 minus the absolute value of VTHP squared. And we would rearrange this guy and just solve for that VSG3 based on what half of our tail current is. And now we know what our DC output voltage is without a terrifying amount of math like we had to do with our other system. So the threshold voltage should be a given value. So usually for a PMOS transistor, it's given as a negative number, so we just make it a positive number, but absolutely, yeah. So the large signal analysis, Hannah, how may I help you? Absolutely, yes, yes. Assuming that, so that's a fantastic thing. So let me write that down up here. So assuming M1 and M2 are matched, and M3 and M4 are matched. So all of our PMOSs need to look like the other PMOSs, and all of the NMOSs need to look like the other NMOSs. Absolutely correct. Thank you for mentioning that. So now let's look at our small signal analysis. There are two ways to do this, one of which is the one that I'm going to do. We're going to make an assumption that's reasonably easy to understand. The other way is to use a whole bunch of Thevenin equivalent circuits that confuses the hell out of me. So that's why I'm not using that one. One day I'll figure out what's going on, but today is not that day. So for our small signal analysis, we need to draw a small signal equivalent circuit for this thing, and it's going to be fairly gnarly. So bear with me here. So I'm going to start with my gate terminal for transistor M1. So let's label this VGS1. Here's GM1, VGS1, in parallel with some resistance R01. And then let's label this node right here, the source of 1, and this node right here, the drain of 1. And then now up above it, make sure I give myself enough room, I'm going to work on transistor M3. So here's R03. GM3, VSG3, and let's see, Here's the source of 3, which we know is at AC ground because it's at our supply voltage. We know that the drain of transistor M3, so this would be the D3 node, is tied to the drain of transistor M1. So I'm just going to tie these guys together with a short circuit here. And then here in the middle is where I'm going to have this voltage VSG3. The gate of 3, so I'm going to call this right here the gate of 3 and 4, is tied to the drain of 3 because we have a diode connection. So I'm going to represent that like this. And now I'm going to work on the right-hand side of my circuit. Right? So here we would have VSG4. GM4, VSG4 in parallel with R0 Once again, the source of M4 is at ground. So this is the node S4. This node right here is the drain of 4. And so I've got that guy taken care of. Down below it, I'm going to put transistor M2. So here's R02 in parallel with GM2, VGS2. Here's VGS2. So this is the gate of 2, the source of 2, the drain of 2. My drains for my NMOS and my PMOSs are tied together. This is the node that I'm taking my output voltage at. We know that the sources are tied together. And let's put an input voltage of 1/2 VIDM on this side and an input voltage of negative 1/2 VIDM on that side. So the assumption that I am going to make, for better or for worse, is that while this circuit is not perfectly symmetrical, in order to make it perfectly symmetrical, I would need to just connect this node to this node. It is very close. So I'm going to say that the voltage at this node is approximately 0. So this is effectively going to be ground. Not exactly ground because it's not perfectly symmetric, but it'll be close enough for what we're doing. Right? When we're perturbing it with a very, very small signal, it'll be okay. And this is avoiding, like I said, several Thevenin transformations that I just can't fully sort out what's going on. We wind up getting the same result, so it's all okay in the wash as far as I'm concerned. Okay, so yes. Yes. Differential mode. Yep. Did I not do VIDM earlier? I just did VID. If I just did VID earlier, I'll just put it as VID. Okay, then let's get rid of the M's just so it's not confusing. Sorry about that. Okay, so we're going to analyze this circuit a little bit differently because it's rather complicated, and because it isn't symmetrical, we can't actually just use a half circuit approach. Okay. So what I'm going to be looking at is small signal currents. So I'm going to call this a small signal current I1 and a small signal current I2 on this side. And we're going to figure out what those are pretty quickly. It should be rather easy. So our small signal current I1 is just GM1 VGS1. And by inspection, the voltage VGS1 is nothing more than 1/2 of VID if we're treating node X as if it were ground, right? So this is going to look like GM1 times 1/2 VID. Over here on the right-hand side, we can say that I2 is GM2 times VGS2. And this is just going to come up being GM2 times negative 1/2 VID. So one thing that I want to point out really quickly here is that if we just flip the direction of that dependent current source, our two currents would be identical, right? So if I2 were pointed up, it is the exact same thing as I1. We'll use that in a little bit. Okay, so now let's sort out a couple of things here. Okay. We're going to focus on transistor M3 for a moment. So in transistor M3, the voltage drop across our current source is VSG3, right? So positive polarity terminal of this voltage VSG3 here corresponds to this terminal of our current source. The negative polarity terminal of VSG3 is tied to the bottom terminal of our current source. So we know for sure that the voltage drop across that current source is just VSG3. There is a linear relationship between the voltage across that current source and the current being supplied by that current source. So it just looks like a resistance that is 1/GM3. It's a diode connected transistor, so that shouldn't be a huge revelation here. So the resistance seen between, or let me put it this way, the small signal resistance of transistor M3 is nothing more than 1/GM3 in parallel with R03. Are we okay with that? So we have a resistance RM3 looking up here between this node and ground. What's the resistance between that same node and ground on the bottom? So I can't say that that current source where I have that small signal current I1 has a voltage drop of VGS1 over it. To me, it looks like it has a voltage drop of negative VGS3 over it, for what it's worth. So the resistance seen looking down, for sure, between this node and ground is just R01. Are we okay with that? Anybody got any beef with anything? Okay. So if I wanted to find the voltage at this node, for the sake of argument, let's call it Vy for now, which is literally just going to be negative VSG3. I could use Ohm's law. So I could say that Vy is going to be negative I1 times R01 in parallel with R03 in parallel with 1/GM3. Are we okay with that? Okay. Substituting things in here. that's going to look like negative GM1 times half of VID times R, not 1 in parallel with R not 3 in parallel with 1 over GM3. And we're going to make an approximation here because we know that R naught 1 and R naught 3 are typically much, much larger than the resistance 1 over GM3. So that leaves us with the voltage at node Y being approximately GM1 over GM3 times 1/2 of our input differential voltage. Yes.
Do you not kind of bring the GM1 into the DGF is not grounded?
Right. So now let's look at what's going on with transistor M4. Okay. So I'm going to define small signal current. I'll do it in red so that I'm consistent here. Of I4, just like I did with my other transistors. But small signal current I4 is nothing more than GM4 VSG4. So my question to you guys is, what is VSG4? Okay, and what's that in terms of VY? Negative VY, absolutely right. So that's just going to be negative GM4 times VY, or substituting in VY, the negative signs are going to cancel each other out. And so I'm going to have GM4 times GM1 over GM3 times 1/2 VID. Now, Hannah, because you mentioned that these transistors need to be matched, what's the relationship between GM3 and GM4 for matched transistors? They're the same thing, so these guys are literally just going to cancel each other out. So effectively, the current, small signal current I4 is the exact same thing as the small signal current I1. So GM1 times half VID. And from here, we can actually figure out what our output voltage is going to be, right? So we know what I4 is. We know what I2 is, or realistically, we could say that I4 is flowing down. Negative I2 is flowing up. So we're going to add those guys together. What's the resistance seen looking into the output node of this guy? In parallel with? So the resistance seen looking down is R naught 2. What's the resistance looking up? R naught 4. Absolutely right. So our output voltage is I4 minus I2 times R naught 2 in parallel with R naught 4, which is going to come out to be GM1 times half VID minus, sorry, GM2 times negative half VID R02 in parallel with R04. Since GM1 and GM2 should be literally the exact same thing because transistors M1 and M2 are matched, this works itself out as positive GM2 times VID times R02 in parallel with R04. And from this, our voltage gain for this circuit, which is just V out over VID, looks like GM2 times R02 in parallel with R04. Now let me ask you guys a question. How does that compare to this circuit if we put some bias voltage on those gates as opposed to using that diode connection? So let's put this in our pocket. Okay. Let's look at the small signal model of this circuit where I'm just grounding these gates because they're just going to be a DC voltage. Trying to remember if I asked you guys to do this for your homework or if it was a BJT version of it. So here's M3, M1, M4, and M2. Is this circuit symmetrical? Perfectly, right? So we can just analyze a half circuit. The half circuit for this guy would look something like this. So let's see. So the gate of 3 would be here at ground. Here's VSG3. GM3, VSG3. R03. Down below here. We'll do GM1, VSG1, R01. VSG1. Here's VN. Tie these guys together. Here's the out one. We okay with that small signal model for our half circuit? Oh, and also because it's symmetrical, we know that this is ground. So what's VSG3? 0, absolutely right. So this is 0, which means this is 0. So the only thing we see looking up is resistance R03. If we were looking for the output resistance looking down from here, what would we see? So the output resistance looking down, we ground this guy out, we look into that terminal, we would see just R naught one. So our R out for this guy right here is simply R naught one in parallel with R naught three. Just for the sake of argument, that would be the exact same thing as R naught two in parallel with R naught four, wouldn't it? 100%, okay? Now let's look at our short circuit transconductance of this guy, because that'll be an easy way to figure stuff out. So here's our small signal I out. So by grounding this node, this whole thing goes away, because effectively we just have the resistance R naught three between ground and ground. Okay. The resistance R naught one is also between ground and ground. So I out by inspection is equal to GM1 times VSG1, where VSG1 is nothing more than Vn. So what's our short circuit transconductance? Just GM1. Okay. So our voltage gain for this circuit is negative GM R out, which is negative GM1. Since GM1 is the same thing as GM2, let's write it as GM2. R naught 2 in parallel with R naught 4, which would have been exactly what we got if we were looking at the right-hand side of the half circuit anyway, right? So what's the difference between this and this? Negative sign, absolutely. So going from a single-ended output, or excuse me, from a double-ended output to a single-ended output actually allows us to convert our inverting amplifier into a non-inverting amplifier. We get literally the exact same gain. It's just now we have a non-inverting version of it. That is the single stage op amp. Yes, ma'am. Sure. Oh, yes, thank you for that. Yeah, 100% VGS1 because it is a NMOS playing fast and loose. Yep. Mm-hmm. Okay. So to solve for V out, effectively all we're doing is we are using Ohm's law, okay? So I'm saying that I have a total current of I4 minus I2 flowing into that node. And there's a total resistance of R naught 4 in parallel with R naught 2 connected to that node. So the total current times the total resistance gives us the voltage at the node. So I think I understand what you're saying. So if we look at this thing right here, so let me do this over here in purple. So we have I4 flowing down right here, right? it's going to see this node, and then we're going to have I2 split off. So that means the current flowing through R02 is I4 minus I2, applying Kirchhoff's current law. Do you concur with that? Now, I would argue that this resistance R04 appears as if it is in parallel with the resistance R02 because it is between this node and ground, and R02 is between that same node and ground. So applying Kirchhoff's current law and then using Ohm's law, we get an output voltage, which is just the voltage drop across resistor R02 in parallel with R04 of I4 minus I2 times R02 in parallel with R04. Okay, I gotcha. So let me see. You're saying you're not catching what's going on here and here. All right, that is fair. Let me think about that. Okay. Let's do KCL at this node. Right here, using this guy and this guy. Okay. So we have a current of I4 flowing in. Right? And we're going to have V out over R04 flowing out. So that represents this current flowing up. We are going to have a current of V out over R02 flowing out. So that's this current right here. You okay with that? And then we also have a current of I2 flowing out. So that looks like I4 minus I2 is equal to V out times 1 over R02 plus 1 over R04, which is the same thing as V out times R02 in parallel with R04 inverse, or V out is equal to I4 minus I2 times R02 in parallel with R04, which is literally the exact same result. So you're 100%, I drew it shittily and explained it poorly, but the result is the same. Yeah, no problem. Noted, thank you. Yes.
Slow down to down a little bit.
Nope. Keep on scrolling or? Okay. So for what it's worth, we are now finished with differential pairs and all of that kind of jazz. So the remainder of this class period, all 30-ish minutes of it, I'd be happy to answer questions about homework assignments and all of that kind of jazz. On Monday, we're going to start looking at our frequency analysis of transistor amplifier circuits. I'm still playing around with exactly how I am going to structure that. So I feel like to buy myself a little bit of time, because I'm not as far along as the notes as I want to be for doing this new way. I might move our deriving our high frequency models up to Monday to give me another 2 days to make out notes so that I'm a little bit more ahead of the material I intend to cover on class that day than literally finishing it the day before. So we're gonna probably cover high frequency transistor models on Monday and then start a generic look at frequency analysis and then look at low frequency for the common emitter amplifier and then high frequency for the common emitter amplifier. So we're going to use those models by Friday at the latest, I think. Freddie, what up? Yeah. So nothing for this because for the most part, we have a simple gain equation and a very simple large signal relationship. So it just kind of is what it is. Yeah, Ryder. Sure. So it's a similar kind of thing here, okay? So if we did, let me do it in orange. So the voltage drop across this resistor right here is Vy. Are you okay with that? The voltage drop across this junk right here is also Vy. So we could say that the current flowing out would be I1 plus Vy divided by R01 in parallel with R03 in parallel with 1 over GM3, which could be rearranged to find that Vy is just negative I1 times that resistance, which is literally what I have right here. So again, explain shiddly, but the math bears out. So I'll need to make some notes in my notes to explain it less shiddly for the next time. Yep.
So would you want it you still have the one the basis of the or what do you call it?
So if we replace these with BJTs, like this V bias right here versus,
Yeah, that's still like
so the diode connection. So you're 100% correct because our base currents are going to be adding a little bit of air, right? Effectively, we would have a circuit kind of similar-ish. So when we were looking at our BJT current mirrors and all of that kind of stuff. That being said, as long as beta is large, it's going to be approximately this because the larger beta is, the smaller the base currents are in comparison to the collector currents that we would be keeping track of. So it wouldn't be exactly this, but it would be something incredibly similar. From our small signal derivation, really the only thing that would change that I can think of off the top of my head would be that the resistance right here would also include a factor of R pi in it, but 1 over GM should still be smaller than all of those things. And so it'll all look roughly the same. Yep. Mhm. 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 Yeah. Pretty much, yeah. So we're looking at things from a small signal perspective. So I mean, the base current is going to be 80 times smaller. The large signal base current is going to be 80 times smaller than the large signal collector current. So yeah. Yep. So for that particular problem, just to be super clear, all I'm expecting to do, and I'm looking at you, Mr. Finch, because you're a stubborn jackass, much like myself, so it's perfectly okay. I'm expecting you to just use the technique that we discussed in class to determine the short circuit transconductance, which is literally just applying an equation, looking at the resistance looking down, which is just an equation that we know, and looking at the resistance looking up, which I don't know that we explicitly covered that, but we definitely covered what it looks like when we have a current source generated by a resistance. And that resistance down there is just going to be R pi 3 in parallel with R pi 4 in parallel with R naught 4 in parallel with 1 over GM4, because it's a diode connected transistor in the Q4 position. So you could derive it if you were so inclined, but we've also seen enough things that look like it, that if we know to just treat that particular transistor as a degeneration resistor, we can use equations without putting in any thought, which is what my intention is. Brody. Yes. I definitely have answers for 2 of them. I just, because I am reassigning 2 problems from previous quarters, I just want to double check things, because after the homework 1 debacle, where I just reassigned problems from a previous quarter and then realized, oh God, like half of these answers are wrong, I'd like to take the time to go through and make sure I'm not just confusing you further. Yeah. We're done. Whatever it's worth. I have been for 15 minutes as far as I'm concerned.